Fantastic. Well, thank you everyone for joining us today. This is Introduction to PASCO Capstone. In the next hour, I hope to introduce you to the fundamentals of collecting data from sensors, visualizing that data, and analyzing it with our PASCO Capstone software. I'm going to accomplish this, I hope, through 3 activities. The first is going to be a straightforward mass on a spring activity, where we're going to talk about the fundamentals of collecting data from sensors and displaying the data from that sensor in a graph display. In the second activity, which will take most of our time, we'll take a look at a more complex experiment, impulse momentum, and there we'll really dive into the controls that Capstone gives you for controlling your measurements, and we'll do a deep dive into analysis of multiple types of measurements. The final activity will show you a completely new way to collect data in a quick investigation of the relationship between gas pressure of a confined gas and its volume. I'll have some interludes throughout to talk about options in Capstone for saving files, sharing data, the types of sensors that PASCO Capstone supports, and some experiment resources so you can get started using Capstone with your students. So a little bit about PASCO Capstone. We're currently on PASCO Capstone version 2. PASCO Capstone is our advanced data collection, display, and analysis software. We have another piece of software for general purpose data collection, particularly in lower grade levels, but Capstone is a more advanced piece of software with more analysis tools and capabilities. It is a Windows and Macintosh application, so you do need a computer to run PASCO Capstone, and it is a licensed software product. There are 2 types of licenses available. One is a single user license, and the other is a site license that's good for you and your students at the site. There is also a free trial available, fully featured for 60 days. So if you don't have a license for PASCO Capstone, you can go to our website and get it. Everything you want to know about PASCO Capstone is on the Capstone product page at pasco.com/capstone. And that includes a link to the free trial, updates, and things like that. More information about Capstone's capabilities, features, and requirements. All right, so I'd like to dive into the mass on the spring experiment. So in this case, we're going to try to answer the questions: how can we quickly collect and visualize sensor data? I'm going to turn on the camera so you can see the physical setup here. And you should be able to see that we're going to use a wireless motion sensor that I have sitting on the tabletop here. The motion sensor has a gold foil here that sends out ultrasonic pulses that can bounce off of objects that are large enough. It listens for the echo from those objects, and from that and the speed of sound, it can determine the round trip time, and from the speed of sound derive the position and some other measurements as well. In this case, we're going to be looking at the position over time of a mass on a spring. In fact, 2 masses. I currently have cumulatively 200 grams on a spring here. The spring's just out of view, but shortly we'll set this in motion, and we're hoping that we can look at the position of that mass over time using the motion sensor and PASCO Capstone. So on to PASCO Capstone. Let's set up Capstone. When you first launch PASCO Capstone, you will create a new file, and you're going to come and see this large white space. This is the workbook space, and this is where we're going to do our visualization and analysis of data. Above the workbook, you'll see some standard file edit menus, the corresponding buttons, and then there are 3 palettes to the sides of the Capstone workbook space. On the left, we have the tools palette, on the right, the displays palette, and below we have the controls palette. And we'll be taking a look at all 3 of those in turn. All right. So when you first open Capstone, by default, it shows you these startup options. These startup options are designed to get you using Capstone quickly in a variety of circumstances. And in this case, because we're interested in collecting data from this motion sensor, I'm going to hover over the sensor data button. And the tooltip tells me that this is going to allow us to connect the sensor and record data in a graph, which sounds great for this motion sensor and our mass on a spring. So I'm going to click on sensor data, and Capstone is going to do a number of things automatically, one of which is to create a full page graph display here, and the other is to open up one of the panels that's in the tool palette. This is the hardware setup panel, and it's opened automatically to prompt us to connect a sensor. Well, I'm using a wireless motion sensor, so what I'm going to do is go to the motion sensor and power it on. It has a battery. I've charged it up, and I'm going to turn the power on for the motion sensor, and it should show up here in the list. By default, Capstone's hardware setup panel is scanning for available PASCO devices. And if I turn on another motion sensor I happen to have in this room, it probably better replicates what you might have in the student laboratory with multiple motion sensors. So this will let us take a look at how we can distinguish between motion sensors to make sure I'm connecting to the sensor or sensors that I want to connect to. So first off, the sensor that is closer to my computing device will likely show up at the top of the list because it has the strongest radio signal, and we sort by strongest signal at the top and lower signal lower in the list. But I can also confirm which sensor is mine by looking at the 6-digit ID that shows up in the wireless devices list and correlating that to the 6-digit ID printed on the case of all of our wireless devices. So in this case, I can see that indeed the top sensor in that list there, oh, me move it closer to my computing device here. The 003183 is the motion sensor that I currently would like to use. So I'm going to click on it, and Capstone will try to connect to it using Bluetooth 4 or Bluetooth Low Energy. Try that again. The wireless line of sensors uses Bluetooth 4, which means we can connect to the sensors within Capstone, and we don't need to go into the system settings for either our Macintosh or Windows computer. So once it connects, it's going to move up to the top of the hardware setup list, which indicates that the sensor is connected, and it gives us some information like the current battery status. Well, I'm only going to use one motion sensor for this activity, but we could connect multiple if we had a reason to. Now that my sensor is connected, I'll collapse the hardware setup panel by clicking on its button, and that reveals in the background that because we chose the sensor data option to start up, Capstone has automatically taken one of the measurements from our motion sensor, the primary measurement, which in this case is position, and plotted position in meters versus time. So the x-axis has defaulted to time. So I think I'm ready to collect data. I'm going to set the mass in motion on the spring above the sensor and go down to the controls palette where you'll see a big red button that says record. I'll go ahead and press record. And now the motion sensor is using those ultrasonic pulses aimed up at the mass and probably hitting the bottom of that lower mass. We're getting position over time, and you can see as the data expands beyond the x-axis scale of our graph, the graph expands with it. So I think I have enough data here. I'll press stop, the button now on the controls palette. And all of the data I collected between pressing record and stop comprises what Capstone calls a run of data. And we can see in the graph legend up here that it calls the runs run number 1, run number 2, and so forth. So we have a run number 1 with a unique color, blue, and we see that data in the graph display. So very quickly, we can collect data from any of these sensors. Now, let's talk about visualizing the data. We saw that Capstone's graph rescaled itself by default to make sure all the data kept in view, but we have manual control over the scaling if we wish. One of the things we can do is take our cursor in the middle of the graph and simply click and drag. And it's as if we're dragging a piece of traditional graph paper on the tabletop here, so we can translate or move this around in space. Now, something we can't do with a traditional piece of graph paper is hover our cursor over the numbers on the X or Y axis and click and drag. And you'll notice that this scales the graph axis of interest almost as if this is a rubber sheet of graph paper. And this works with both the numbers on the X axis and the Y axis. So by clicking and dragging to move and clicking and dragging on the numbers on the axes, we can rescale the graph and get the view we desire. If you happen to be using a mouse with a scroll wheel, or you have a trackpad with a scrolling feature, here's a handy trick for zooming in. I can put my cursor over a data or anywhere in the graph, and I can scroll my scroll wheel to zoom in and out, and it will always scroll in and out relative to the point where my cursor is. This same trick also works over the axes. So if I want to scale only the y-axis, I could hover over it and scroll up and down, similarly over the x-axis. So many ways to manually change your view of the data in a Capstone graph to make sure you're looking at what you're interested in. All right, so now let's take a look at how we can automatically change our scaling. A lot of times the goal of the graph is to see full screen all the data that we've collected using all of the space available in the graph. So for that, we're going to go to the graph toolbar. There's a set of tools up here in the graph toolbar. By the way, if you're off of the graph like I am now, the toolbar is not visible by default, but as soon as your cursor goes over the toolbar, it pops up to be visible. I'm going to hover my cursor over the first or leftmost button here, and you'll see that there's a little tooltip that pops up and says that this leftmost button, which is called Scale to Fit, does the following action. It scales axes to show all data. So I'll click on that, and you can see automatically these axes have scaled and the graph is panned so that my data essentially fills the graph screen, which is often what you want. This button works during data collection, after data collection, to make sure you're looking at all the data that's being collected. Now, it's important to note that many of the buttons in the graph toolbar are two-part buttons, and the Scale to Fit button is one example of that. The button has a icon on the left portion of the button. That's what scaled the graph. And there's a drop-down arrow. That little arrow to the right portion of the button is options for that tool. In this case, the Scale to Fit button has only one option. I'll click on that downward arrow, and it says this option is to auto scale from 0. If I turn that option on, and now press Scale to Fit, because the auto scale from 0 is on, you'll see the origin included in my graph. If I wanted to turn that option off again, I'll return to the drop-down right portion of this button, click on it, and turn off auto scale from 0, and the behavior is back to the default of filling the screen with the data. So there are a lot of tools in the graph toolbar that have these two-part buttons. The statistics tool, the Greek letter sigma, is another example. The left portion of the button, in this case, I press it depresses, turning the statistics feature on. In this case, you can see it shows me the mean, the default statistic, visually on my graph display for this entire run. So the mean value of position was 0.27, but the statistics button also has a drop-down. And if I click on the drop-down, you'll notice that it shows me other options for which statistics I could use to analyze my data. I can turn on as many or as few of these as I wish. So I could turn on minimum, maximum, mean, and I'll turn on standard deviation. And now when I click away, you can see that it's doing the analysis of all 4 of those that I selected using the drop-down. The left portion of the button still toggles the statistics feature on and off. In this case, I'll turn it off to keep things clean, but it's important to understand this 2-part character of many of the buttons in the graph toolbar. Typically, the left portion turns something on, the right portion, the drop-down, gives you options for that tool. All right, so I think I'd like to collect another run of data. I had 100 or 200 grams rather cumulatively on the spring. I'd like to change that. So I'll turn my camera back on and I'm going to remove one of these 100 gram masses. So this next run will be with merely one 100 gram mass on. It's going to go up above your view, but trust me that I've just set the now 100 gram mass in motion. And if I want to record a second run of data, make sure my motion sensor is well aligned, I'm going to return to the controls palette where I have the record button. I'll press record again. And now we can see we're collecting another run of data, which calls run number 2. And you may notice that it supersedes run number 1 on the graph at least. So I think we have enough data there for run number 2 with a different mass. And I want to ensure you that run number 1 still exists in our file. One way I can confirm that is to go where the data and measurements in the file live, no matter whether or not they're being displayed. And that's back in our tools palette, the data summary panel. So I'll click on data summary. And here you can see in the sensor data summary tab that I have my wireless motion sensor offering actually 3 measurements: position, which I've looked at, and it also recorded other measurements from the sensor, velocity and acceleration, which are actually derived from position. But even though I wasn't looking at those measurements, it recorded runs 1 and 2 for all of those. Now, one of the things you can do in the sensor data summary is rename runs by double clicking on them. So I might rename run number 1 to indicate that this was 200 gram mass, so I can remember later on. And similarly, I'll double click on run number 2, and this was merely a 100 gram mass. And as I hit enter now, notice in the background here that my changes to run names propagate throughout the file. So any displays that are showing that data automatically get the change that I make in the data summary, which is where the data and measurements actually live in a Capstone file. All right, so we're done with data summary for now. I'll collapse it by clicking on the data summary button in the tools palette. And we're back to looking at run number 2. And a natural question at this point is, so how do I see run number 1 in my graph? Well, we're going to use another 2-part tool in the graph toolbar. This looks like a rainbow triangle. It's called the data selector button. And I'm going to begin with the drop-down portion of this 2-part button, which gives me the opportunity to select which of the 2 runs so far that I've collected is visible. So you'll see I toggle between these 2, and by default, it shows only 1 run at a time. So I'm switching between run 1 and run 2. Natural question is, can I see both at a time for a better visual comparison? The answer is yes. For that, we're going to use the left part of the data selector button. And if I hover over it, you'll see that the left part allows simultaneous viewing of multiple data sets. I'll click on it. The data selector is now turned on. And now when I return to the dropdown, I'm able to turn on 1 or more runs, however many I desire. If your goal is to show all the runs you've collected, the select all option at the top of the menu is a shortcut to doing both of those things, depressing the button on the left and selecting all the runs. So clicking away now, we can see I'm looking at both runs number 1 and number 2 with my 2 different masses in this experiment. We can see some differences, including the average height of the spring. I'm going to show you one final thing before we proceed, and that is it's important to know a concept called which is the active run. So I'm going to return to the graph toolbar and introduce you to a new, very powerful tool. It's called the fit tool, the curve fit tool. I'm going to go directly to the drop-down portion of this curve fit tool to show you that we have a lot of possible fits in Capstone, from proportional and linear to more complex fits like Gaussian. And if you don't see a fit here that you need, there's even a user-defined fit, so you can make any fit that you can conceive of. In this case, I'm going to choose a fairly complex one, but one I think that's appropriate for this, and that's a damped sine fit, so an exponential times a sine fit. And if I click on it, you will notice back here that it has applied a curve fit quite successfully to one of the runs. In this case, it was run number 1, this colored run here, where I had the 200 gram mass. Now, why did it choose run number 1? Well, this gets to the concept of the active run. By default, only one run in a graph is active, and tools like the curve fit tool apply to the active run. How do you know which run is active? Look to the graph legend and you'll see that the background of one of our runs is shaded. In this case, run number 1's symbol has a shaded background. That indicates that that run was active when I turned on the curve fit, and thus the curve fit applied to it. A natural question at this point is, how do I make the other run active to analyze it? There are two ways to do that. One is to click on its symbol in the graph legend. You'll notice the background shading switches to run number 2 when I do that. I'll go back to run number 1 to show you a second way. If I wanted to make a particular run active, I go over the graph and simply click on a data point, and that's the same effect as clicking on the symbol of that run in the legend. So now if I return to the curve fit tool and turn on that same type of fit, a damped sine, you'll see that I have now successfully fit both of these curves, both of these data sets rather, with a curve fit, the damped sine fit, which seems to work pretty well in both cases. So that concept of the active run is an important one once you've made the decision to look at more than one run at a time. The graph defaults to showing only one run at a time to keep things clean, but oftentimes we want to visualize the differences between them by looking at multiple at a time. In that case, it's important to understand this concept of the active run. Now, one other thing that's not well known is you can actually select more than one run to be active. One way to do this is to shift click on other symbols, and that will select contiguous ones. A quicker way is to click on the header for the column of the run symbols. In this case, I click on X, all the runs become active. And now when I return to the curve fit tool, for example, to turn it off by clicking on the left portion, that applies to all, or in this case, both of the active runs. All right, so that is connecting a sensor, choosing a sensor data path, which gets you a graph of the default measurement, and collecting multiple runs, renaming them, and understanding how to do analysis on these multiple runs when we're looking at both of them at the same time. All right, I do want to address a couple of common questions at this point, and that is one of which is, it chose a measurement position. That's kind of the default measurement for the motion sensor. If I wanted to change that, I could simply hover over the y-axis label, which is actually a button, and I could choose a different measurement like velocity or acceleration. Instead of doing that, I'm going to show you that although the x-axis of the graph defaults to time usually, I can also change it there. So I might change the x-axis by clicking on the x-axis measurement time to something like velocity, and now I'm looking at something like a phase plot. So change the axes as you need. The x-axis defaults to time, but you can always switch it to whatever measurement you're interested in, and Capstone will take care of the correlation between the y and x measurements. All right, one final feature, my favorite thing about Capstone. We hope Capstone can be used by you and your students in the lab to experiment about the world around you, but we also hope you're comfortable experimenting with Capstone itself. And one thing that makes that feasible is there's unlimited undo in Capstone. So we encourage you to experiment with whatever feature you're interested in, because using this button up here, you can undo as far back as you wish. So I'm going to do a few undos here. Then I'll show you can also access undo via the edit menu. And there's a keyboard shortcut, Control Z. So I'm going to press and hold Control Z, or if I'm on a Mac machine, Command Z, and I can undo all the way back to the beginning of this file. I can also redo, that's Control Y on a Windows machine. So I'll press and hold Control Y, and I'm now fast forwarding through every single step that I've shown you in Capstone. So we hope this undo feature, unlimited undos, encourages you and your students to be comfortable just playing around with the buttons, seeing what things do in Capstone. So I'm now back to that final state of my experiment as I redid everything. Now, if this were data I want to preserve or do further analysis on in the future, I would want to save it, giving me the opportunity to reopen it. The most comprehensive way to save a Capstone file is to save it as a Capstone Workbook file. I can go to the File menu and choose Save Experiment. And when I do that, it opens up either the Windows or Mac file save dialog. I'm going to save this to my desktop, and I want you to notice that Capstone files are saved with the extension .cap. So it saves it as a Capstone experiment file. This is masses on spring data. And it's going to save it as a .cap Capstone file. This does mean you need Capstone to open it, but it does preserve everything about the file: the sensor setup, the displays, the data you've collected, and any analysis. So I'll save that to my desktop as a Capstone file. And now if I want to reopen this, it would come to the same state. If I wanted to share it with Jonathan, whether he was on a Mac or Windows machine, I could send it to him. He could open it and continue analysis or further data collection. So saving a file as a Capstone file .cap via the File menu is the most comprehensive way to save everything about the file. All right, if you truly want to get back to the starting position though, I'm going to turn off the motion sensor. We're done with it for now. You can start a new Capstone file by closing Capstone and relaunching it, or more directly by going to the File menu and choosing New Experiment. Capstone likes to have just one file open at a time, so it closes the previous file, offering to save it if you hadn't saved it already. All right, let's talk a little bit more about Capstone here. We've looked at one option for saving from Capstone. This is the most comprehensive, but it does require Capstone to reopen the file, and that's saving it as a .cap Capstone experiment file. We'll look at 3 different ways throughout today's presentation on how to share data from Capstone. All right, a little bit about sensors for Capstone. I showed you the wireless motion sensor. Wireless sensors are generally white, like the sensor you see on the screen here. They use BLE or Bluetooth Low Energy, Bluetooth 4 to connect directly to Capstone inside the application. No need to go into the system settings. We have, however, produced motion sensors for many, many years. Starting around 2001, we had the Passport line of sensors as USB became ubiquitous. It's important to note that Passport requires some sort of Passport interface to connect to the computing device. It doesn't connect directly, but the good news is that all the Passport sensors are compatible with PASCO Capstone. We work hard to continue supporting those sensors that are in the field. You can even go back to the last millennium, sensors older than most of your students, and the Science Workshop line of sensors, when you have an appropriate interface, also work with PASCO Capstone still. You can learn more about the 3 sensor lines and all of the sensors within these lines for making measurements across the sciences by going to pasco.com/sensors. All right. Let us jump now to the next experiment, which you can see set up here in the background. I'm going to use this time a smart cart, and on the smart cart I've attached a spring plunger. I'll talk a little bit more about that as we get set up. I have it on a level track, and I'm going to push it down to the end of the track that you can see in the far corner there to kind of measure the behavior of the cart as it undergoes a collision with that end stop. Talk more about the experiment in a moment, but first, what are we trying to do in this experiment? Well, in terms of learning Capstone, I'd like to show you how we can control sampling options in Capstone to better ensure that we capture data of interest. And we're going to look at a much deeper analysis of the data and look at some ways that we can report that data out. All right, so on to Capstone. I've started a new experiment file. This time around, I'm going to go directly to hardware setup and open the hardware setup panel in the tools palette. And my motion sensor is still on. I'll turn that off. It doesn't matter if it's on or off, but I'm going to return and turn on the wireless smart cart, which, despite being red or blue, is a wireless sensor in the line of typically white wireless sensors. We have blue and red to help you distinguish them in experiments like conservation momentum when you're using more than one. I'm going to click on Smart Cart to turn it on. It shares that property of having a 6-digit ID. And once it connects, we're going to see that I call the Smart Cart a sensor, but it's actually a suite of sensors. It's a wireless device that has 4 different sensing elements in it. So once it's connected, it moves to the top of the list here, and we can see there are indeed 4 different types of sensors in the smart cart. A little bit more about the first 2. The smart cart has wheels with an optical encoder, and that determines the cart's position and velocity and acceleration. So that's the smart cart position sensor. I have attached this heavy spring to the end of the smart cart where there is a force sensor. The smart cart also has a 3-axis acceleration sensor built into it and a gyro sensor if you're interested in rotational velocity. But in this experiment, we're going to focus on measurements from the first 2. So for the sake of convenience and for reasons you'll see later, I'm going to choose to turn off the sensors that I'm not using, in this case, acceleration and the gyroscope. I can turn off sensors completely so that they're not broadcasting data in the hardware setup panel by clicking on this little toggle, and I'm going to turn off acceleration and gyro from the sensor. So we won't be getting data from those. Otherwise, we would be getting data from all the sensors that are not turned off, whether or not we were looking at that data at the time of recording. All right, so we could continue with sensor data, but I want to introduce you now to the displays palette along the right side of the workbook. This gives you more control over what sort of displays you'd like to use to look at data or even introduce things like images, movies, and text. So if I hover over the graph display, which is what I'm most interested in here, you'll see I get a tooltip that gives me 2 ways to add the graph display to my experiment. One is to drag to the page, and the other is to double click. So I'm going to double click on the graph icon, and we'll see that that creates a graph display occupying the entire workbook space by default. I have the opportunity now to define what I want to be on the axes. For the y-axis, I'll click on the Select Measurement button, and I'm going to start by looking at the force. That's the force where I have that spring bumper attached to the end of the smart cart. Now, I think I'm on the right track here. I'd like to do a test run just to see if I am set up to properly record the force as I collide the smart cart with the end stop at the end of the track. So I'm just going to hit record in a moment, and then I'm going to push the cart along the track, let it collide, catch it on the way back, and press stop. So we'll look at the force versus time data that I collect from that sequence. All right, record, push, grab, and stop. All right, so I'm going to expand here by scrolling on the x-axis. Go here a little bit. The interesting part here looks like it happened at about 2 seconds. That's 2 seconds after I hit record. And it looks like I captured, well, 1, maybe 2 data points during the collision. You'll see that otherwise the data is pretty close to 0. So it seems that the force during the collision was measured by just these 2 data points. If I zoom in a bit, you'll see that those data points are, see, 0.05 seconds apart. So this collision happened quite rapidly, and I only got a little bit of data during the collision, so I'm not particularly confident that this is a good representation of force during the collision. That's one problem we'll solve in a moment. The other problem is a little more subtle. I'm going to scroll into the y-axis here, and you'll see that while there wasn't a collision, that is before and after the collision, my force sensor was reading close to 0, but not quite 0. It was about 1/10 of a Newton off. So we're going to fix both of those problems, not collecting enough data during the collision and the force reading not being 0, by addressing those in the controls palette. So I'm going to head down to the controls palette, and we're going to take a look at what we can do here besides recording and starting and stopping the recording of data. First thing I'd like to do is figure out how can I get rid of that offset? That is, how can I zero the force sensor? So my cart is on the track now. I have the attachment of interest connected. I want to have the cart in the same orientation as my experiment when I zero the sensor, because it's sensitive enough to detect whether something's hanging off or pushing in. So I'm going to go down to the controls palette with the cart in the right orientation, and I'm going to choose the measurement for the smart cart's force sensor by switching this toggle. So I'm now looking at the settings for the smart cart force sensor, and you'll see to the right here I have a 0 button. So I'll press 0, and at this point it's taken whatever small offset there was and it's zeroed that out, or tared this force sensor. So I'm good in that aspect. Next up, I want to choose what the sample rate is. That is, how often the sensor records data. Now, how often was the default? Well, the smart cart's force sensor defaulted to 20 Hertz, or 20 samples per second. Now, that wasn't quite enough for this very short duration collision. So I can come in and I can choose to have a common sample rate between sensors, but this is a fairly unique experiment in that I want quite different sample rates for my force sensor than for my position sensor. I'll talk a little bit more about that in a bit, but to set different sample rates, I'll start with the force sensor, and with the force sensor selected, I'll go ahead and scroll up on the sample rates, and I'm going to choose a sample rate that I know works pretty well for this configuration, 500 Hertz, or 500 samples every second. Now, this is one reason it was good to turn off those measurements I'm not interested in, because I want to optimize and maximize the bandwidth of that Bluetooth connection for the measurements I'm interested in, because I'm going to be sampling at least one of them very fast. Now, for the position sensor, I'm going to change the sample rate there to be different. I'll increase it a bit to about 50 Hertz. This works fine because I'm mostly interested in what's the ingoing velocity during before the collision and what's the outgoing velocity afterwards. It doesn't really matter during the collision. All right, so I've set those two things in the controls palette, two of the things you can do to make sure you're getting the data you want. There's one more thing about the controls palette that will be convenient now. I collected a run number 1 that was just a test. I don't really need it anymore because I figured out my problems. So I'm going to go to the delete last data run button. I could click this, or there's a drop down that would let me delete particular runs if there's more than one, or all runs. But since I have only one, I'll press delete last data run. It's a quick way to get rid of that data from the data summary and throughout the file if you're just collecting data that you don't really need. All right, so I think I'm ready with force. I've set the sample rate for both force and my position measurement from which I want to derive velocity, but I want to look at velocity while I'm recording it. So I want to figure out how to look at both force and velocity against time. Now, it would be natural to say, you know what, if I want another graph display, let me go and double click displays, and I could make this have a y-axis of velocity. That will work fine. There are a couple downfalls to this, though. One is these time axes are not synced up. These are completely independent displays that could be showing different measurements, different runs even, different time scales. So I'm going to undo that, Control or Command Z, until I'm back to a single graph display. You might remember that the tooltip for the displays said you could also drag and drop. So I'm going to drag the graph icon out, and when I hover over these blue boxes, it gives me a preview that if I drop the graph display at this point, how it's going to configure it. So I'm going to drop it below the existing graph display. This is looking more promising. I could set that second graph display to velocity, but I still have a bit of a dilemma in that this is still a separate graph display. It has a separate time axis. It would work, but probably not the best. So I'm going to undo that and show you that when we're dealing with graph displays and multiple measurements, it's usually best to have what we call multiple plot areas within a single graph display. So I have one graph display currently with one plot area showing force versus time. let me show you how to add a second plot area. I'll do that by going to the toolbar and clicking on this button that says Add New Plot Area. Alternatively, you could go down to the x-axis, and this button does the same thing. So I'll add a new plot area. I'll define the y-axis of that new plot area to be velocity. And now I have what I want. I have two y-axes for force and velocity, and I have a single shared time axis, so I can scale them together in time. So that looks like what I'm aiming for. I'll go ahead and collect another run right now. I'm going to press record. Remember, we're going to record a lot more data this time at higher sample rates. And I'll do the same thing, push the cart, let it collide, and then stop data collection after the collision. So record, push, and stop. All right, so this looks promising. I'm going to scroll on the x-axis where the collision happened. And indeed, the force versus time plot shows us we collected many data points during that collision because of the higher sample rate of 500 hertz. It also shows us that we can determine the change in velocity, if that's what we're interested in, from before the collision to after the collision, even though it had a slower sample rate in this case. So let us look at those two things. I want to show you one other thing. If you're interested in swapping the positions of these two plot areas, you could change the y-axis measurements, or you could turn on the rearrange feature for a moment. Our problem is our hand by default is moving the plot area contents. We could instead make our cursor switch plot areas by turning on that button. I could drag the force plot area to the bottom, leaving the velocity at top. And now I'll turn off the rearrange button. And now I think I'm ready to start by analyzing the change in velocity. I'm going to show you a new tool. It is called the coordinates tool. As the name implies, it's great for finding coordinates. But before I do it, we have to now recognize that when we have a graph of multiple plot areas, we need to know which of the two plot areas is active. This harkens back to the dilemma we had before when we had a graph with two runs. We had to know which is active. How do you know which plot area is active when you have more than one? Well, there's a very subtle blue line that is around the active plot area. If I click on the lower plot area, you might just be able to see that blue line around the force versus time plot area. If I click on the upper plot area, that blue line goes around that. So if I want to use the coordinates tool on the velocity time upper plot area, I first click on it to make sure that it is the active plot area. And now I'll go to the tool bar, click on this coordinates tool that looks like a crosshair, and there's a drop down that actually offers me a couple of ways to use coordinates. I'm going to choose just the standard coordinates tool, and that drops a gray box in my active plot area. The coordinates of the gray box are shown by this label, and you can move the gray box anywhere to update those coordinates. Most usefully, you can bring it near a data point, and if you're near a data point, that arrow shows you that when you release, it's going to snap on to that data point. And now the color of this, it's no longer gray box, it's a box that has the color of the run, tells me that I'm actually looking at the coordinates of this gray box's data point. I could scroll left and right here, or I could move the gray box, but I'd like to look at the velocity before the collision. I think that's distinctly before the collision, and we can see that the incoming velocity was 0.864 meters per second before the collision. Well, I want to determine the change in velocity, so it's natural to say, let's add another coordinates tool. I could, of course, return to the toolbar to add that, but there's a quicker way, and that is to know that some of the tools that we access a lot are available more directly by clicking directly on a data point. You'll temporarily get a pop-up of some commonly used tools, one of which is the coordinates tool. So instead of adding it via the toolbar, I click on a data point directly, and now I can choose the coordinates tool. I get the same tool, I can still move it, but it saves me a bit of time because it started on the point of interest where I clicked. Now, if I wanted to find the change in velocity, I could simply do the math myself, but if I don't want to do that, there is a hidden feature of the coordinates tool. To do this, I'm going to delete one of my two coordinates tools here by clicking on its label and choosing the X. That leaves me with a single coordinates tool, and here's the secret. It's the delta tool for determining changes. If you click on an existing coordinates tool, one of the tools that pops up is called delta tool. So click on a coordinates tool, you get the delta tool button, turn on the delta tool, and you now have a second handle that you can drag anywhere on the graph. For example, snapping it to another data point. And now the delta tool shows me the change in the X coordinate, time in this case, and Y coordinate, velocity, between my two handles. So in this case, I can see that the change in velocity was negative 1.694 meters per second. Why negative? Well, the smart cart has a convention here that is on its label. So all the forces, accelerations, positions are measured with X being positive to the right. We can change that, but it's synced up between the force and the position sensor. So I'm going to keep And that's the reason we have a negative velocity. It's also, of course, the reason we have a negative force, which seems to correlate well. All right, so we've determined the change in velocity from which we could get information about the change in momentum. Let's look at how we can look at impulse. Impulse is the area under the curve, or in this case, above the curve, between the curve and the y=0 axis. And to find that, we're going to essentially integrate using the area tool. So first, I'll make the lower plot area active, and now I'll introduce you to the area tool in the graph toolbar. Because the lower plot area is active, it applies to the lower plot area, and it tells me the area between the curve and the x-axis. Now, I'm going to zoom in here to show you that it's doing it for the entire run, even those little jaggy bits there. If I wanted to confine my area analysis to just the collision, I need to somehow figure out how to tell Capstone to analyze only this section. The way to do that is called the highlighter tool. So with my lower plot area active, I'll go up to the graph toolbar and turn on this highlighter, which drops a box on my graph. And you'll notice I can resize the box, I can move it around, and only those data points highlighted inside the box are analyzed by the area tool. So I'm going to adjust this box and move it around until I'm confident that I'm looking only at that section during the collision. And now it tells me that the area or impulse for that region is a negative 0.86 Newton seconds. All right, so I think we have the fundamentals here of the data we want to analyze. What could we do with this? Well, we could write it in a lab notebook. We could type it somewhere else. I'm actually going to begin recording it inside Capstone itself by creating a table. I'll drag a table display down below my existing graph display. I want to have the table smaller than the graph, so I'm going to hover between the two where I see a dashed line, and I can dynamically change the relative size of these two displays with that handle. Now I'm going to be using this table display here to record these values and the scenario in which these values were recorded. So I'm going to just double click in the first cell of my table here, first column, first cell, and I'm going to begin typing something. This is going to be a label about what I was doing. So this was hard spring, 1 bar mass. This was a slow collision, relatively slow. So I'm going to hit enter, and you'll notice that it says, you're typing data in a table, you must want user data. I'll tell you that tables can have sensor data, but when you have hundreds of data points like we do here, I tend to not use tables. I do use them quite often when we just have a few data points like I do for my metadata I'm collecting here. User data 1 is not a great name, so I'm going to click on it and choose rename, and this is basically the trial. I'll hit tab. I don't have units, so I'll delete that. And I now have a column of user entered data, which is basically describing the conditions under which the other measurements were collected. Now, I want to record the change in velocity here in the second column, so I'll double click and simply start typing negative 1.694 for my analysis. Hit enter. It creates another user entered data set, which I can rename as change in velocity, however verbose or concise I want to be. If I want to be really concise, I can right click and insert the delta character for change. There are a lot of things you can do in Capstone by right clicking. That's delta V, hit tab, that was in meters per second. Now, I would also like to record the impulse in a new column. I'm out of columns by default here, but I can go to the graph toolbar. This leftmost button is going to insert another tool, or another column rather. And for this, I'm going to start typing the area or the impulse, negative 0.86. Hit enter or click elsewhere, and I'll rename this to be J, the impulse, and the units as shown there in the area tool are Newton seconds. All right, so we can actually begin collecting data inside the Capstone file itself, kind of as a metadata table. Now, I've done this already. I don't want to belabor collecting more data, but if we wanted to change conditions, like make a faster collision or change it from being a hard spring to a soft spring or even a clay bumper, I could do so. I did that before our session today, so I'm going to go and open up that file so that we can jump directly to further analysis. So here's some pre-recorded impulse momentum data using the same setup. All I did was vary how fast the cart was moving and what implement was on the force sensor. So hard springs fast, soft springs fast and slow, clay bumpers. So I've merely filled in this table using the 6 runs I collected and analyzed in the graph above. Now, I'd like to actually see if we can discover a relationship between the change in velocity and the impulse. This page is pretty busy. In Capstone, we can add additional pages within our workbook file, and we can do that by going up to the workbook tab showing I'm on page number 1 of my workbook, and I could click on the new page button. I will click on the new page button, and it adds a page number 2. Now, here's a trick for saving some time. I would like this same table on the other page, so I'll click on it, click on its border, and go to Edit, Copy, return to page 2, edit, paste, And I now have, at least as a starting point, that same table of results. I'm going to add a graph, not a graph for my sensor data, but a graph for my metadata. I'll drag that above the table, and now I'll assign this measurement y-axis to be not a sensor measurement, but a user entered data set, the impulse. And I'll change the x-axis to be another user entered data set, the metadata of the changes in velocity. And here we can see a pretty clear relationship is revealed between the impulse and the change in velocity. It looks a little odd because of those connecting lines are connecting in time. So I mentioned right-clicking. I'm going to right-click on the data point here, and I can turn off this feature for show connecting lines. If you want to change many graph properties, you can go to the properties button, but a few are accessible directly via right-clicking. So now that I have a pretty linear looking relationship, I'll return to our curve fits and I'll turn on a linear fit. And here I see the correlation coefficient indicates a pretty good fit linear relationship between the impulse and the change in velocity. And in fact, the M there, M being slope, is about 0.505. I happen to know that my cart mass is about 250 grams. I added a nominally 250 gram bar to it. That spring may add a little bit. So I'm beginning to suspect that this M, though standing for slope, might also represent the mass of my cart system. If I wanted to take some notes within Capstone, I could actually go add another display. This is a text box. I'll drag and drop it here to the right of my table, and I could begin typing my results or my comments. It looks like J, the impulse, insert special character, is proportional to delta V with a proportionality constant of mass. So we seem to be trending toward this idea, for which we could do further experiments, that maybe J is equal to MV. I can italicize these by using these settings. And now we begin to see this relationship that we're discovering between the impulse and the change in momentum. All right. So that's a pretty in-depth analysis with multiple runs, trial table where we've collected the data and done a further graph, not of sensor data, but of our data. But hopefully this shows you that you can do some pretty deep analysis. And we've also controlled the sample rates and zeroing to make sure we're collecting what we want. I'm going to save this Capstone file. I'm going to save as, since I started with a different Capstone file. And this is impulse momentum data. And at this point, I chose to do further analysis in Capstone, but sometimes you may choose or want to do analysis elsewhere. So let me show you two ways we can get just data out of Capstone. In this case, with my trial results table, I'm going to click in the table, hit Control A or Command A on a Mac to select all the data, and hit Control C or Edit Copy. And now I've basically copied all the data within this table, which is great for pasting into data analysis programs and spreadsheets like Excel. So here's all that data copied from the table in Capstone, pasted into a different program. Now, if you want to export more data and data that's not in the table, Capstone does actually have a formal export of data, file menu, export data. And this lets you choose different data formats, comma separated values, the default, tab delimited is an alternative, and you can choose all the measurements that you want, sensor measurements, user entered data, run numbers, and you can customize what you're exporting by using this export data option. Now, I'm not going to do that in this case, but I want to note that all you're going to get is the exported data, none of the displays, none of the analysis. But if you're using Capstone in a particular experiment just to get the data, the export data option in the file menu will allow you to do that. All right. So a little bit more about Capstone. We've looked at saving the entire Capstone file. We've looked at exporting the data for importation in a data analysis program or spreadsheet. We can also copy and paste data from a table. We'll look at one other option in our last activity, which is gas pressure and volume. So let me show you what I have set up here for gas pressure and volume. Quick tabletop experiment that uses the wireless pressure sensor. And what's neat about this is it uses an accessory that comes with the sensor, and that's a 60 milliliter syringe that I've attached to the wireless pressure sensor with about 30 milliliters of room pressure air. All right. So what are we going to do in this activity? We're going to determine how we can figure out the relationship between a sensor measurement, the wireless pressure sensor will tell us the pressure being read, and something that we're getting from the real world, not from a sensor, but the volume that I can read off of the syringe. So this is going to be user entered data that I get off the syringe and type into Capstone, correlated with pressure measurements read from the sensor itself. So let's see how to do this in Capstone. I am going to turn off my smart cart, go to the File menu, New Experiment, and let's go directly to Hardware Setup once again. If I click on it and turn on my pressure sensor, it should show up in the available wireless devices. I'll click on it, and it should connect using BLE or Bluetooth 4. And I'll just note in data summary, the pressure sensor offers only one measurement, pressure. So it's not as complex as something like the smart cart. All right, I'll close the hardware setup panel. And now we have the option of creating our own displays from the displays palette or using one of these startup paths. I'm actually going to show you that these startup paths are a little more subtle than just pressing the button. We started the first activity by pressing sensor data. When we did that, there were actually some alternative options. If I click on the drop-down arrow here, you'll see that the first option, continuous sampling, is what defaults to just pressing the big button. But I have alternatives like manual sampling, which I'm going to use in this case. I'll explain why. But the tooltip here tells me when I hover over manual sampling, this is for graph manual sampled sensor data versus user entered data, which sounds perfect for this example of pressure from the sensor and volume typed in. Now, when I do this, it creates a table, graph display, but I want to show you there's no magic behind this. I'm going to undo, and if I wanted to set that up myself, I could double click a table, I could double click a graph, and I could assign the measurements, for example, pressure here. The only new thing here is that if I hit record in a default new file, it records from a sensor at the default sample rate, which for the pressure sensor is 20 Hertz, way too fast for me to manipulate the syringe to get those volumes. So the real trick here, the only thing that's new, is I can switch the sampling mode from continuous to what's called keep mode, also called manual sampling. And when I'm in keep mode, I can record data at my leisure. So whenever I'm ready to record a pressure, like I've switched the syringe to the right volume, I can hit the keep button, change parameters, hit the keep button, and so forth. So that's the only thing that's magical behind the scenes here. I'll undo until we're back to the startup options and show you that is done for you when you click on the sensor data dropdown and choose manual sampling. All right, the only thing I need to do is define what X is. In this case, it will be the volumes from the syringe. I'll hit tab. Because the syringe is demarcated in milliliters, I'll choose that for units. And notice that I'm already in keep sample mode. So I am ready to collect data by using that sensor data path and knowing that the dropdown lets me choose manual sampling. How do we do manual sampling? Well, I'll hit the preview button. Since I'm only one person here, I'm going to type in my volumes ahead of time. You can do this at any time, including during data collection. But I'm going to go at 5 milliliter increments from 60 down to about 15, which I know is pretty tough to do with only one hand here. So starting at 60 milliliters, I'm at 60, and notice that I get a preview of the sensor reading. It's a preview. I can change it slightly. You can see it's live, and only when I press keep will it be recorded and change to black, indicating it's actually a recorded value. So I'm going to begin to speed through these, and I'll go down to 55, press keep. I'll go down to 50, press keep. And what happens if I press keep twice? Looks like I made a mistake here. I can always go back if I'm still recording, and it looks like I didn't go to 45. So I'll click on this cell. I'll go to the intended volume, 45, and I can now press keep to record the correct 45. Shortcut here, since I don't have 3 hands, I can click on the cell, and now the enter or return key on my keyboard is equivalent to keep. So I'm going to do that for the rest of the values. 35, it's now neutral at 30, pushing it in at 25, 20, now it gets tougher at 15. All right, so I did that kind of rapidly, but looks like we got some sort of relationship here. I'm going to press stop to end this recording. And again, all the data between pressing record and stop is a run. And I see it demonstrated here on the right side. So looks like we don't have a linear relationship. What sort of relationship? Well, if we look at the curve fits, there are some candidates here. Perhaps this is inverse square. I can look at that, looks okay, but I can turn on multiple fits at the same time. So I might compare inverse to inverse square. And it looks like, except for that errant data point, inverse is a much better fit both visually, and the root mean square to error is lower. So I'm going to turn off those fits and revert to looking at the inverse fit. So I think we've begun to perhaps discover that there's an inverse relationship between pressure and volume. And it looks like the pressure, the y-axis, is equal to A, some constant here. Now, remember I recorded the volumes in milliliters? Capstone's smart enough to know that, hey, milliliters is probably a volume. Do you want to convert that? So even though I did specified it in milliliters, it knows how to convert it to liters. So if I wanted more standard units for my constants, I could do that. So pressure is equal to A some value over volume in liters plus some small offset B, which is pretty close to 0 in the scale of things. So looks like we've discovered an inverse relationship between pressure and volume. That's not the only way to do it, though. If you wanted to only focus on linear relationships, which some pedagogical approaches do, we could do something else. So I'm going to open the display palette here. I'm going to drag in a completely separate graph. You might say, why not a separate plot area? Because I actually want the x-axis to be different. But I'm first going to replicate the graph on the top, pressure versus volume in liters, and then show you that if you're interested in transforming axes on graph measurements, you can do so quickly through a feature called the Quick Calc. If I want to transform this volume to perhaps the inverse volume, I'll click on the label, but instead of choosing a different measurement, I'll go up to the Quick Calc flyout menu, and I can choose to square, cube, square root. In this case, I'm going to take 1 over that. I'm going to make the inverse, and you can see that linearizes it fairly well. How linear is it? Well, I'm going to right click and turn off show connecting lines, turn on a linear fit. And we can see that our correlation indicates we have a pretty good indication of an inverse fit here by linearizing or taking the inverse of one of the values here. So no matter which way you want to approach it, you can see you get similar results, discovering the relationship between pressure and volume. Now, we have a few more minutes here. I want to show you one other thing. If this is an inverse relationship, other instructors might take the approach of saying, hey, if it's truly inverse, then pressure times volume should be a constant. I'm out of columns here. I could add a new empty column in the table, but there is a special button that lets me add a new column, which is a calculation based on other columns. So I'm going to add a new calculated column, change the relative size of things here. And in this new column, I would like to have a calculation. And much like Excel, when I add a new calculated column, it gives me a bar up here. I'd like this to be the pressure times the volume. How do I get volume? Well, if I right click, I can insert data, including user entered data. I'm going to calculate it in liters. And if I hit enter, it will do the calculation of pressure times volume, which I can designate as PV. And since I did the unit change, this is in kilopascals times liter. How close is that to a constant? Well, I'll turn on the table tools. I can get to them. This issue earlier today. Maybe I'll get back to them in a moment. Looks like I can't select it, so let me see if we can refresh that. No. Well, the table tools, there it is. The table tools has a statistics button, and in that statistics button, we can choose min, max, mean, and you can see it's pretty close to a typical value here, kind of confirming in a third way that we have an inverse relationship. Well, I'm going to save this file as a Capstone file with all my data. This might be gas pressure versus volume data with data. And again, that's a Capstone file, so I can open it up and continue analysis because it's a complete preservation. So let's wrap up by talking about some sources of experiments. Before I do, let me show you one more way to get data out of Capstone or information out. If I wanted this graph revealing the relationship between pressure and volume in a report, I'm going to click on the border of the graph and choose Edit Copy and head over to, say, a document. Here's a Word doc. And I can go in here and paste, and it will paste an image of my graph display. Now, it's important to note this is just an image. All right, it's exactly as it was shown there. I can't do further analysis here, which is why it's good to have saved the Capstone file if I want to go back and adjust things later. So the third thing we can do is take an image of a display by copying and pasting. All right, where to get experiments in the 5 minutes we have left? Well, one thing is you can create your own. We've built a few on our own. Oftentimes you're using the sensor data option, or you're creating your own displays using the displays palette. I want to show you a variation on this theme though. I spent quite a bit of time in Capstone setting up this file, and I may not want my students to spend that same amount of time setting things up. So one thing you can do is set up the file yourself, collect the data as an instructor, and then say, looks like this file is working. I'm going to turn off the things I want students to do. I'm going to turn off the fits. And most importantly, I'm going to go and delete all the data. Right. I now have a file that has manual sampling set. It has all the displays. It even has the user entered data. And I might go in and say, I'm going to save this as a different Capstone file. Maybe this is gas pressure and volume template or config file or start here. But I can give this to my students, and they now don't need to spend the time setting up the displays and configuring other things like calculations. It all depends on how you want to use your lab time. So you can create your own files, or students can create their own. One thing the sharp-eyed among you might have noticed is that when I connected the pressure sensor, Capstone actually intimated that, hey, Boyle's law is pretty popular, so I'm going to do a new experiment with the pressure sensor still connected. And as soon as it sees a wireless pressure sensor, it says, oh, I have a quick start file built in. There are no instructions here, but if I choose the Boyle's law quick start, it opens up a configuration which is already pre-configured with volume, for example. So look for quick starts for popular experiment setups in Capstone. The final thing and the most comprehensive is our free online PASCO experiment library. You can access this at pasco.com/freelabs, or if you're starting from the PASCO website, front page, you can go to resources, experiment library. And here you can filter out from over 1,000 labs. If I am a college instructor of physics looking for a capstone experiment on Boyle's law, I might choose these filters, and it filters it down, Boyle, I think, because of the apostrophe. It filters it down to 2 college physics labs we have there. If I click on any one of them, it will go to the dedicated experiment page. And here, because I'm logged in with a free PASCO account, I can see both the teacher files with data and the files for students, of which there are basically 2 types. There's a Word doc, if you want to edit, or a PDF, which you can print out or provide electronically, which is printed instructions, more traditional instructions for creating the file and doing the analysis and collecting data. And also in the experiment library for this file is a different way to do an all electronic file, and that's a Capstone file. So I'm going to download this Capstone file, return to Capstone and close it, so I have only one file open. And I'll open this Capstone file that I just downloaded from the experiment library for Boyle's law. And when I open it, you'll see this is what we call a Capstone Workbook. And this Capstone Workbook contains not only displays for data, but also instructions and images to get students doing the lab and answering questions, all within the Capstone Workbook. So we looked briefly at adding a text box to the Capstone Workbook. Imagine if an author of the Boyle's Law lab added images, potentially videos, instructions, and places for students to answer questions. It's going to open up this larger file because of the images contained in it. And once it opens up, you'll see that we have all the instructions for doing the lab contained within the Capstone Workbook on successive pages of the workbook. So everything from setup to the procedure, including live data displays embedded inside the workbook. So if you go to the experiment library and look, especially for higher end Capstone experiments, you'll often encounter 2 versions: the text-centric version you can edit as a Word document or print out as a PDF, and the Capstone-centric version, which is self-contained within PASCO Capstone. Well, we are 1 minute away from the end of our time. I want to thank you so much for joining us today. If you have further questions, I encourage you to contact your local PASCO rep, whether in the US or globally. Going to pasco.com/support will get you in touch with them. That same webpage includes information about contacting PASCO technical support and customer service if you have questions from them as well. So thanks so much for joining us today.